Welcome to Chapter 6, Advanced SQL. We will be learning in this modern database management systems how to work with advanced SQL in this lecture in specific. This is your Professor Atif Fareed Mohammed. We'll be defining the terms associated with advanced SQL, write single and multiple table queries using SQL commands, define 3 types of join commands and use SQL to write these commands. Write non-correlated and correlated subqueries and know when to write each. Write queries to create dynamic and materialized views. Understand common uses of database, triggers and stored procedures. Discuss the SQL 2011 and SQL 2016 standards in SQL enhancement extensions. Very often, the data we want to see from a query needs to come from multiple tables. Most of the time, these tables are linked in relationships via primary and foreign keys to implement one-to-n or one-to-many relationships. The vast majority of joins involve matching primary and foreign keys, but there can also be other kinds of joins as well. So there's a join, equijoin, natural or inner join. The join is a relational operation that causes 2 or more tables with a common domain to be combined into a single table or view. Equijoin is a join in which the joining condition is based on equality between values in the common columns. Common columns appear redundantly in the results table. Natural or inner joins are equijoin in which one of the duplicate column is eliminated in the result table. The outer joins is a join in which rows that do not have matching values in common columns are nonetheless included in the results table, as opposed to inner join in which rows must have matching values in order to appear in the results table. Union joins include all data from each table that was joined. It's pretty much like a set union. Unions are not literally joins, and syntax for expressing a union is not the same as the syntax of expressing a join. Nevertheless, unions are also combine data from different tables. In the Venn diagram, the data from each table is represented as a circle. Natural joins will only return records from each table that have a match in the join condition with the other table. This is also called an inner join. By contrast, with an outer join, the records from one table will be included, even if there are no corresponding records from the other. With the union join, all records from both tables are returned. This can also be accomplished via full outer join. This is an ER diagram from Chapter 1. Each of these entities, including the associative entity, is implemented as a table in the database. So we have customer, order, product, and order line. And these are, as we are discussing this quite extensively, the Pine Valley furniture. So this is a good example to understand how the joins work. Customer T and order T have a one-to-many relationship, as you can see from the customer ID foreign key in the order T or order table. These are 2 of the tables. The others are order line table and product table. Order table has a foreign key called customer ID. This foreign key references the customer T table's primary key, also called customer ID. These tables are used in the queries that follow. This is an equijoin. Notice that the customer ID is shown from both tables. It is probably not necessary to see this because they are always matched. Notice also that 10 rows are returned in this query. There are 10 rows in each order T table, and only those rows from customer T table with corresponding orders will be included. That is because equijoins are inner joins by default. The query is a select customer T dot customer ID, comma order T dot customer ID, which should be the same, customer name, comma order ID from customer T, comma order T, where customer T dot customer ID is equal to order T dot customer ID, order by order ID. The results come under the customer ID, and customer name, order ID, and then the whole result is given in front of you. So for join conditions, sometimes the syntax is used instead of where clause. This way you can distinguish between conditions that are used for matching records between tables versus conditions used for selecting which rows to return, as we learn about chapter 5. A join involves multiple tables in from clause. The on clause performs the equality check for common columns of the two tables. So note that from 6.1 figure, you see that there are 15 customers, but only 10 of them have links with orders. Therefore, only 10 rows will be returned from this inner join. So this is a good example, and the SQL is given right in front of you to look at, and this will give you the inner join results in terms of a table. So list the customer name, ID number, and order number for all customers. Include customer information even for customers that do not have an order. So we have applied left outer join clause here that causes rows from first mentioned table customer to appear even if there is no corresponding order data. Unlike the inner join, this will include customer rows with no matching order rows. For the tables in figure 6.1, this will return 16 rows. That is because there are 15 customers and one of these customers have 2 orders. So hopefully this is explaining you in a little bit depth how the joins actually work. Here is the result. You can see the contemporary casuals is 1001, and that's order again at 1010. So note the 2 rows for customer number 1, contemporary casuals. Also note that several customers don't have orders. This is because of the left or outer join. There are 4 tables involved in this join. Therefore, there are 3 join conditions in general. If there are n tables, there will be n minus 1 join conditions. The final condition, where order ID is equal to 1006, is not a join condition. This is the condition that restricts the number of rows returned, not one that connects tables. This is why the join syntax, inner join, outer join, may be preferable using that syntax. Join conditions are clearly distinguished from other conditions. So customer is 222, customer name is value furniture, value furniture, value furniture, and then customer address is given as below. And you can see that all rows returned from this query will pertain to order ID 1006. Note that the full query results include columns from 4 different tables. So what are the employee ID and name of each employee and the name of his or her supervisor? Label the supervisor name as manager. So you can see the result of this query, which is given on the screen. The same table is used on both sides of the join, distinguished using tables aliases. See the next slide for details. Suppose that you have a table of 5 employees as shown here. Only one of these employees has a supervisor. The employee supervisor column would be the foreign key in the employees table, which is associated with the primary key employee ID. We saw an ER diagram showing the same sort of thing in chapter 2. So a self join is associated with unary relationship here. Subqueries are usually placed in the where or having clause of the outer query. In this case, the subquery results are used to test a condition for the outer query's where or having clause. If the condition is a test comparing the subquery result to another value, then the subquery should return a single value. One row consisting of one column, if it is used in an in test or all the tests of a where clause, it can return a list of values which are multiple rows, each with one column. If used in an exists test, there is no limit to the rows and the columns returned from the subquery. It is also possible to put subqueries in the form in from clause of an outer query instead of a table. In this case, there is no restriction on how many rows or columns should be returned from the subquery, but the subquery's column must be consistent with the columns in the select clause of the order query. If the subquery is used in the select clause, the subquery's result should be single value, and this value becomes a column of the outer query. When using multiple tables, sometimes you need a subquery, sometimes you need a join. Other times the problem can be solved by either subquery or a join. It is also possible to combine joins and subqueries together. First, the subquery returns customer ID for the order ID 1008. That the value is then used in the where condition of the outer query. Note, since the where clause is testing for equality, the subquery must return a single row with a single column. Note that the subquery is embedded between the parentheses. So this is something that you must be mindful when we are embedding any query, that must be within the parentheses given. Sometimes you can accomplish the same result in different ways. The previous subquery could have been done via a join. The join query, as given on this screen, will also generate the similar results for the order number 1008. The joining technique is useful when the data from several relations are to be retrieved and displayed and the relationships are not necessarily nested, whereas the subquery techniques allow you to display data from only the tables mentioned in the outer query. For example, with the join, we could see that order ID but not the subquery. A join involves a cross product which combines all combinations of rows from each of the tables, followed by removing the rows that don't match according to the conditions of the join. A subquery operator operates differently from a join. First, subquery executes, which returns a result. Then that result is used in the outer query. So for these examples, although the results are same, the execution that gave the results are quite different. Correlated subqueries use the result of an outer query to determine the processing of the inner query. That is, inner query is somewhat different from each row referenced. In the outer query, in this case, the inner query must be computed for each row processed in the outer query, whereas the earlier examples, the inner query was computed only once all the rows processed in the outer query. Note that the outer query uses product T with a PA alias in its from clause. The subquery also uses product T in its from clause but not the PB alias. The subquery also references the PA alias from the outer query, which makes subqueries correlated, and the query is given here for you to review. Correlated subqueries are a powerful feature in SQL that allow us to perform more complex and dynamic comparisons within the queries. Unlike regular subqueries, which are independent and can be executed on their own, correlated subqueries depend on the outer query. This means that the subquery can reference columns from the outer query, enabling us to compare each row in the outer query with a calculated value that is specific to that row. One common use case for correlated subqueries is when you need to compare individual values with aggregated data, such as averages or sums. For example, you might want to find employees when who earn more than the average salary of their department. In this scenario, the subquery calculates the average salary for each department and the outer query compares each employee's salary to this average. This allows you to identify high earning employees within each department rather than just across the entire company. Another useful application of correlated subqueries is when you need to compare individual values with related data from another table. For instance, you might want to find customers who have placed orders with amounts greater than the average order amount. In this case, the subquery calculates the average order amount for each customer, and the outer query compares each order amount to this average. This enables you to identify high value customers based on their order history. Overall, correlated subqueries provide a flexible and efficient way to perform complex comparisons and analysis within your SQL queries. The key feature that identifies the correlated subquery is the fact that the subquery makes reference to the column from the outer query as mentioned earlier. Note that the order line T is a table used in the from clause of the outer query but is not a table in the from clause of the inner query. Yet the where clause of the inner query does refer to a column from order line T, especially the product ID. If your subquery has a reference to the table in the outer query, that makes it a correlated subquery. If it does not have such a reference, then it is a non-correlated subquery. Here the subquery is testing for a value that comes from the rows processed in the outer query, specifically the order line T table, which is the from clause of the outer query, but not the subquery. The exists operator will return a true value if the subquery resulted in a non-empty set. Otherwise, it returns a false. So the subquery processing, as mentioned here, is clear in terms of select distinct customer ID from order T, whereas the select customer name from customer T where the customer ID in, and then the subquery kicks in. That actually brings all the details out for us. In this case, the subquery will execute once for each row of the outer query. In this example, the outer query goes through each row of an order line T table. Each time it gets to a row, that particular row's product ID is used in the subquery to get the product of the particular order line. There are 17 other line records, so the subquery will execute 17 times for each order line record. So you can see the difference in behaviors of correlated versus non-correlated queries. With the non-correlated query, the inner query executes once and then the outer query executes. For the correlated subquery, the outer query executes, and for each row, the inner query will execute once. So you have seen that the first order ID selected from order line T is order ID 51001. The subquery is evaluated to see if any product in the order has a natural ash finish. Product 2 does, and the part of the order exists is valued as true, and order ID is added to the results table. The next order is selected from the order line T is order ID 51002. The subquery is evaluated to see if the product ordered has a natural ash finish. It does. Exists is valued as true, and the order ID is added to the results table. Whereas processing continues through each order ID, where orders are 1004, 1005, and 1010 are not included in the results table because they do not include any furniture with a natural ash finish. Here we have a case where the subquery is from the clause of the outer query. This is often called a derived table because normally you see the tables in the from clause because aggregate functions cannot be done in the where clause. It is often useful to use subqueries when you want your conditions to include aggregate results. For example, this query would not have worked. Select product design, product description, comma product standard price from product T, and where the product standard price is greater than average product standard price. So instead, we do what the slide is showing, and you see the results. This query determines the customers who has in a given line item purchased the largest quantity of any Pine Valley product, and customers who has given line item purchased the smallest quantity, and returns the results in one table. The use of union clause: each query involved must output the same number of columns and they must be union compatible. This means that the output from each query for each column should be compatible data types. So although those queries involve subqueries, this is not necessary for the unions. It just so happens we are doing it in the example given here. It is possible to use union with many different select statements. Here we perform a single union operation combining just two of them. Another feature of this example, it is possible that select clause to include literal values in its returned column list. See the words smallest quantity and largest quantity. These are not values in the tables but can still be shown in the results. SQL does not include the if-else statement. Unlike procedural programming language, the case keyword was introduced to accommodate this need. The case syntax has the possible forms. The case form can be constructed using either an expression that equates to the value or a predicate. The predicate form is based on three value logic: true, false, don't know, but allows for more complex operations. The value expression from queries are matched to the value expression. So these are the first two forms. Null if and chorus are the keywords associated with the other two forms of the case expression. More complicated SQL queries. Production databases contain hundreds or even thousands of tables, and tables could include hundreds of columns. So sometimes query requirements can be very complex. Sometimes it is useful to combine queries through the views. If you use a view, which is a query, you could have another query that uses the view as if it was a table. Here are some examples of creating view, which will be a permanent object in the database like a table. Then we use the view as if it is a table. We discuss views in more detail later in this chapter. The view is called T-sales and consists of aggregate query involving a join of three tables. T-sales return the total sales of each product sold by each salesperson. The query below, it uses T-sales as it were a table. Note that this query involves a correlated subquery. This query shows the biggest selling product for each salesperson. So hopefully this has given you some decent understanding of the view. It is important to test your query against a set of test data that includes unusual data, missing data, impossible values, etc. Subqueries can be very useful, but can also cause computational overload. This is especially true for correlated subqueries. Suppose, for example, you had a correlated subquery where the outer query was processing through 10,000 rows. This means the subquery would execute 10,000 times. So in fact, that one overall query involves 10,001 real queries. This is another reason it is important to test your queries, but not only must they be able to execute, but they should produce valid results in a reasonable time frame. So guidelines for a better query design: understand how indexes are used in query processing, keep optimizer statistics up to date, use compatible data types and for fields and literals, write simple queries, breaks complex queries into multiple simple parts, don't nest one query inside another query, don't combine query with itself, if possible avoid self joins. All options are not available with every DBMS. For each DBMS has unique options due to its underlying design. You should refer to reference manuals for your DBMS to know which specific tuning options are available to you. Views provide users controlled access to tables. The term base table refers to the table containing the raw data. So a dynamic view is a virtual table, whereas the materialized view is an actual table generated by copying data from the base table queried. Some sample create command is given on the screen, so you can look at that. This view has a name, so create view expensive stuff underscore v. It's a view. View is based on select statement. Check option works only for the updatable views and prevents updates that would create rows not included in the view. Although views assist with data security, don't rely solely on views. For security, there are more important security measures. Advantages of dynamic views: use processing time each time view is referenced, may or may not be directly updatable. As all SQL constructs, you should use views with discretion. Routines and triggers: routines are the programs modules that execute on demand. Functions are routines that return value that take input parameters. Procedures are routines that do not return value and can take input or output parameters. Triggers are routines that execute in response to the database event, insert, update, or delete. Procedures and functions are called explicitly by the users for the database. For example, an application program, when calling a procedure or function, you may pass it parameters. Functions, unlike procedures, will actually return a value in both cases. There could be several queries or updates done to the database. Triggers are not called explicitly, instead, they are invoked as a result of some sort of database action, such as inserting a new record, modifying an existing record, or deleting a record. They could also be invoked as a result of DDL, data definition language statement, to alter table. Triggers may occur either before, after, or instead of the statement that aroused the triggers is executed. DML or data manipulation language triggers may occur on insert, update, or delete commands. The stored procedure code: create or replace procedure. You can look at this example very carefully because this is important if you are ever going to use the SQL 2011. You need to be creating routines in that. The example of data definition language trigger is given here for your view, and call the procedures given here also. All these tables and views are used internally by DBMS, but you can also query them. For example, you could find the owners of the company's tables. Here is an example of if PVF or Pine Valley Furniture's database was stored in an Oracle DBMS. SQL enhancement extensions: user-defined data types, UDT, subclasses or of standard types or an object type, analytical functions or OLAP, online analytical functions, procedures that has ceiling, floor, SQRT, rank, etc. New data types can be big int, multi-set, collection XML. The create tables like create a new table similar to an existing one and merge as we discussed earlier. SQL enhancement is continued, programming extensions are needed, persistent stored modules are needed, and the capability to create draw drop code modules are needed. And I would suggest you to read rest that is provided in the book for you to go through. Again, this work is protected by United States copyright law, so be mindful when sharing this with anyone. Happy learning. See you in the next lecture.